Good afternoon. Today we're going to start to learn about simple linear regression, which is the case where we are analyzing data and we have a continuous predictor and a continuous response. Remember, last time we've been looking at only discrete predictors, continuous responses. Now we're going to look at the case where the predictor can be some continuous value as well. So, simple linear regression involves pairs of observations, and we have pairs of observations xi, yi, where xi is my predictor or independent variable, and my yi is my response or dependent variable. So what we're interested in doing is taking my data set with all of these predictor variables, all of these response variables, and saying, what is the relationship between these two? As my predictor xi changes, what happens to my response yi? So, as you might guess from the term linear regression, we're going to think about these as a line. So what we're going to say is that each observation yi can be described by this line equation. And now, what we're going to say is that this y is equal to some constant, beta 0, plus some other constant, beta 1, times this predictor xi, plus some random noise terms, epsilon sub I, and epsilon sub I have a normal distribution with mean 0 and variance sigma squared. Now the reason I used a different color for this is we're kind of thinking about this as a theoretical sort of model. It says, like, in truth, across all of the data, there is some true linear association between these, but we don't know what beta 0 and beta 1 are, and therefore we can't observe these epsilon sub i's either. So you think of these as something unknown. What we will do, however, is look at some methods for estimating what these coefficients are, and then making some deductions from there. So what we want to look at next is we want to think about how exactly are we estimating these beta 0 and beta 1. These are some unknown constant, and we need to come up with some estimate of them. So you could think there are many different criteria that we could use for trying to estimate these. But the criteria that we want to use is we want to minimize this L, which stands for likelihood. And what we're going to do is we're going to minimize these epsilon sub I squareds. So in other words, we want to pick our coefficients beta 0 and beta 1 such that these epsilon sub i's, the square of these errors is minimized. You can obviously think that the lower this sum squared error, the better my estimates here will be. So you can see, if you're interested in more details, you can look in your textbook, chapter 2, that lists some details about how exactly this gets minimized. But suffice it to say that we could rewrite this epsilon sub I involving, I could isolate this epsilon sub I on one side of the equation. So I could say yi minus beta 0 plus, or I suppose the minus would carry through, minus beta 1 xi squared. So in other words, I want to pick my beta 0 and my beta 1 to minimize this expression. And what you could find the details of in the textbook is how exactly that minimization is conducted, and it's what you are probably already familiar with from calculus. We take the derivative of this expression with regard to the partial derivative of this expression with regard to beta 0, the partial derivative of this expression with regard to beta 1. That's going to give us two equations, both of which are set equal to 0. So then we're going to have two equations in two variables, beta 0 and beta 1, and we're going to be able to solve this to get an exact solution. So in other words, there's nothing numerical going on, there's nothing random going on. It's the solution of two equations in two variables. It has some exact best solution. And we'll call that solution, I'm going to use a different color now, we're going to call that solution this best estimate that I get. We're going to call these beta 0 hat and beta 1 hat. So that beta 0 and that beta 1 is what comes out as the solution of this minimization and solving to find the roots of that equation. So when I use some statistical software, it's going to give me these best estimates. It's going to do this machinery, do this optimization for me, and it's going to give me what these estimates are. So now what that tells me is now I have an equation for what my line is. Now my equation for my estimated regression line is this theoretical line that we had before. So I have my y sub I, except now I'm going to plug in this best estimate of this intercept coefficient beta 0, and then I'm going to plug in my best estimate of the slope of this line beta 1 times my xi, and now I have these terms called EI, which are my residuals. So these EIs are what are called residuals, and these EIs you can also see if you plug in, and let me take a step back here. Let me take one step back and say, actually the estimated regression line would be y equals beta 0 hat plus beta 1 hat xi. So my predicted response, what I think the response will be at a particular value of my prediction xi, is substitute in, and really this shouldn't even have an I there, really this should just be x. So what we're saying is, for any prediction, no matter what value my predictor takes on, I can come up with the estimated response y by just substituting into this equation for the line. Just say it's this beta 0 coefficient plus beta 1 coefficient times whatever my x is. That then leads to this expression, where really I want to say each pair of points xi, yi satisfy this expression now. So in other words, this is the equation for my best fit line, and then from my actual data, I can say how far off is this actual data point y from the predicted value. So these e sub i's are called the residuals, and what you can see between this equation and this equation is that these e sub I residuals are actually equal to what the observed response yi was minus the prediction of this ith point. So let me draw you a picture that will hopefully clarify what's going on here. So let's say I have my x and my y, and in my data I should make these points a little bit bigger. In my data I have all of these different data points, and I observe the x and the y for each. And I'm interested in fitting the best line through this data. So the best line through that data might look something like that. Okay. So now, the equation of this line is exactly y equals beta 0 hat plus beta 1 hat x. It's exactly this. This is the equation of this best fit line. So of course, the beta 0 here is my y-intercept. So in other words, if this had extended all the way down here, this point would be my beta 0 hat. And this beta 1 is the slope of this line. So namely, for every 1 unit change in x, my y changes by beta 1 hat. Now let's consider one of these points. Let's consider this point. So I'm going to call this specific point, I'm going to call this the xi, and I'm going to call this the yi. Okay. So I'm just looking at a particular point and saying what is the value of the predictor, what is the value of the response. Now, what this yi hat is, says this yi hat is for this particular response xi, what did I think, what was my best estimate of the response? And it's exactly the y value at this x point. So in other words, it says take this x point, and what was the value of the line for that x? That's my yi hat. So now this difference right here, this difference between what I predicted and what I observed, is my ith residual. So again, what we've done is in solving for this equation of this line, we've fit the line that's going to minimize the sum of this squared, how far is this point from this, is each point from this line. So let's look in a little bit more detail at what these coefficients are. So as I said already, this beta 0 hat is the intercept of this line, and this beta 1 hat is the slope. So this beta 1 says for every 1 unit increase in x, on average, and this marker is dying, let me switch colors. For every 1 unit increase in x, we expect beta 1 hat increase in y. So this regression really serves two purposes. If you think about analytics, you think about it as descriptive analytics, describing what already exists in the data, predictive analytics, what do I think will happen in a new case, and then prescriptive analytics, which says what should I do about that? How should I change something in my system? So this regression actually solves or works to address both of the first two. This linear regression is descriptive in the sense that it explains the data we've already seen, it explains the best pattern, and these coefficients go to answering that. This describes the best pattern that I've seen, that as my x is increasing, my y is also increasing by this much. But it's also predictive in the sense that if I now pick a new point, so if I pick some point maybe right here, maybe I'm interested in saying I have not observed any x right here, what do I think the response would be for that particular value of the predictor? Then this regression says, here's what I think the response would be. Here's my best guess. So it's predictive in the sense that give it something we have not seen before, and it makes a prediction, it makes an estimate or a best guess about what this response would be. So one thing that we will see when we start looking at computer code for this, which we'll do in class on Friday, we'll start to see that when we do this in software, there will be a hypothesis test associated with each of these coefficients. So we will see a hypothesis test, and the hypothesis test, the null hypothesis, will be that the true value of this coefficient is equal to 0, and the alternate hypothesis will be no, it's not equal to 0. Likewise, we'll have a hypothesis test on this beta 1 coefficient. Is this beta 1 coefficient equal to 0, or is this beta 1 coefficient not equal to 0? So the p-value associated with these hypothesis tests is going to let us judge whether this is a good relationship or not. So if we get a really small p-value that says that's strong evidence to reject the null hypothesis, meaning this is strong evidence that the true coefficient is not 0, so it's a good predictor in my model. If I get a p-value, say let's look at this term, let's look at this slope coefficient. If I get a p-value that's pretty high, like 0.4, 0.5, then that says that's not enough statistically significant evidence that this true coefficient is anything different from 0. That means this whole model is kind of useless. It would say if this coefficient was not significantly different from 0, it would essentially say there's no relationship between my predictor and my response. When we start talking in class next week about multiple regression, which is where we have still just one response y, But then we have multiple predictors, so I could have x1 and x2 and x3. I could be trying to make this prediction using lots of different inputs. Then we'll be assessing this hypothesis test for each of these predictor variables to say, is each of these variables contributing to the model or not? And if we get a p-value that's pretty high, it will say there's no relationship between the response and this particular predictor, so I should not include it in my model. That's all I have to say for right now. If you have any questions, please post them to Notebowl. Otherwise, we will pick up in class on Friday.